This is a bit of fun. Normally, previous years, I've started by giving a talk about our applications, but Tom already gave a great introduction to MD and everything, so I'm not really going to talk about that. But this is a topic that we started with in this school a few years ago, and that deals with everything else. Not necessarily the gory acceleration of GPUs and everything. I'm more than happy to talk about that, in particular the HPC challenge. But this is partly a very practical talk to try to help you write better code. And write code that is professional. And I would argue that this has developed tremendously in the last decade or two in the HPC space, partly because there's so much more competition from business and everything. So what is software engineering? So this is very much based on experience from our big code GROMACs that we've developed over 25 years. And by any standard here, we've been moderately successful and everything. The problem here is that this is a gigantic code base, 3 million lines of code. And what happens with code bases of this size, not just GROMACs, is that, that you're successful, you have a release every year or 2 years, but at some point you suddenly realize that things are slowing down because you're spending more and more time fixing bugs and everything. So that for every release, we probably spent 3 months stabilizing it, and that time kept going up. And if you're then doing 1 release per year, you're spending a quarter of your development time just fixing your own mistakes. And that is simply not sustainable long term. And we had, at the time we were using horrible source repository in CVS, we had old style build chains, I'll come back to and tell what that is. And we were still using bug tracking, and then we had a very fancy state-of-the-art artificial intelligence testing system that were us doing things manually. So this talk is partly going to be based on some lessons that we did some 8 years ago, and trying to do things seriously and be really serious about software engineering. That I think has helped us tremendously, at least, that it's also helped this code to be, well, more productive in the sense that we develop code quicker, we develop code of higher quality, and we get more releases, and that has also helped us get quite a lot of funding for developing the software itself. So if we take a step back here and say software engineering, there is a definition of this, and rather than trying to read that by heart, the whole idea is to apply an engineering approach, not just to the code you're writing, but how you're designing code. What is it that you want to achieve? Can you guarantee the quality of your code? And can you guarantee that what parts of your code might be susceptible to a bug, for instance? If somebody finds a bug in your code, do you know that whether it's your code or the compiler or the hardware? And to try to have systematic approaches to all this, which is not entirely easy because it was certainly new to us at the time. To think about this, I think most of you are just as me, have a scientist mentality in the background. You're probably trained in one of the applications. You care deeply about proteins in my case. I care about short-term deadlines. I want those papers published. I want my students to graduate. We want to get that grant. And hey, new code, that's a new fancy algorithms. Awesome, we could use that in a paper. And then I write more code than I read. And in particular, once we've written the code once, that student graduates and will never look at the code again. So at the time we recruited a postdoc who was, well, he wasn't trained in software, but he became trained in software. And his approach to this is very much in the software engineering instead. And software engineering is pretty much the opposite. The single most important line here is code equals liability. Because any code you take on in a project is not just code that you have to write, you will have to maintain it. In every release, you will have to debug it. You will have to make sure that it's correct and everything. And there is some hard trade-offs here. And in particular, you need to get used to deprecating code and removing code that should no longer be supported. And this can easily lead to some friction in the groups. But I would argue the one thing that has made us successful is that we've moved over from the scientist mentality to the software engineering mentality. These are the rules we live by. Just because a random person on the internet has some fancy algorithm that they would like to donate to our code, my typical answer is no thanks. Because unless this is an exceptionally valuable algorithm that I know that we will have funds to support in the long term, we can't take on that liability. The point is that if you don't take that approach, you are taking on technical debt. And there is a beautiful definition of what technical debt is. Technical debt is exactly the same thing as monetary debt. Just as you take on a mortgage, that's perfectly fine. But when you take out debt, that will incur interest payments. Perfectly fine to pay interest if you're willing to keep paying interest. And that the interest you're going to keep paying is that you will have to keep debugging that code and fixing the old code. And if your old code is full of hacks, you're going to be fixing those hacks in every single release. If you have n files and every file depends on every other file, that's now an n² dependency. And as n grows, that's going to become more and more and more painful, and that's where we were. And at some point in life, you will have to choose. Either you keep paying this interest. You could, of course, choose to take on more credit card debt. I would argue that's what most developers do. And at some point, you're going to go bankrupt in the sense that you will no longer be able to maintain your code. It will die. Other people will stop using your code because it's so horrible and buggy. Or you can decide that you're going to start doing this thing the right way and reduce your debt. That's going to be boring initially because you're not going to feel as productive. But before you know it, you realize that if you don't have to pay this interest, you will have a whole lot of more money or development time that you can use to actually do productive stuff. The other reason for this is that this is actually fun. Last year, there was a very high-profile story. I'm not sure, those of you who are in physics might know David Chandler. David Chandler was the guru of the hydrophobic effect and everything. And there was a long story on supercooled water, and I won't have time to go into the details, but it turned out that after 7 years, people eventually found out that there was a bug in the code from Chandler's group. And this was code they had refused to share for 7 years. And it's sad because Chandler died roughly 2 months after they finally found out, but it very much tarnished his reputation. The question is, do you want to have a profile like that? It's easy to say that your code is not good enough to share yet or something. Do you want to be the person responsible that your entire team has to pull a Nature or Science paper? And do you want that on your CV in science, that, oh, we should never hire Erik Lindahl because he was that sloppy guy that forced us to pull that code? Or do you want to be the person that does things the right way? And if you want to do things the right way, the point is that you should have open software. Not because I care about the openness from a political point of view and everything, but more open software means more eyes looking at my code and identifying my bugs. And proper software engineering means that we have proper tests and everything. That means I can't guarantee that it's free of bugs, but at least I have a setup that means that we get rid of the bugs as quickly as possible. There are hundreds of tools you can use here. I will not go through all of them, but I'm going to talk a little bit about not so much planning, but starting with the build phases here. Good tools that will help you build better quality code. And then I'm going to talk mostly about continuous integration. How do we rapidly get things in? Real continuous integration would be all these web services nowadays where 10 seconds after you've written a code, it can actually go live on a web server. And then I might talk a little bit about deployment and continuous feedback. But mostly, I'm an old HPC buff, so this is going to be how we try to apply these tools to old style codes. Last year, I took this Laplace code actually. So I created a small, tiny repository that you can download. There are links to this on the site too. And you can use this as a template for your code. Not only can you use it, I think you should steal this unless you're already doing this. It's deliberately a tiny repository that makes it trivial for you to clone and then just replace the source with your own stuff. That makes it easy to get started. Once you get it started and you realize that you need more advanced stuff, and rather than reading all the documentation, you're more than welcome to steal things from GROMACS. There are tons of other codes out there too. Just look at other open source projects and say that if you need a way to identify whether the compiler supports AVX instructions, search for it on Google and steal the code to do that elsewhere. There are hundreds of projects available. Our code, I updated the statistics. So last week, there were 49 commits, 183 files changed, and 5,375 lines inserted while I was on vacation. I have not kept up with all those 5,400 lines. And if you look at just since January 1st, there are like 157,000 lines added. The lines deletions, that's temporary. This is not entirely trivial to keep up with. And you can imagine the number of bugs that could be created with a development pace like this. If you've probably all been there, right? That the version that it worked last week and now there is something wrong. Or it worked last night and then you had 14 different versions and you happen to overwrite the version that worked and everything. Suddenly it doesn't work when you enable optimization. These things happen. There are ways to get around this. The first obvious thing is that you're going to use source control. How many of you are using Git? Awesome, I hope so. So I'm not actually going to spend much time on the Git slides. You all know that what Git gives you, and I'm going to jump straight ahead to one more recommendation, how to organize your Git workflows. The traditional way that most, because it's coming from CVS, is usually that you use many different large branches, and you could have one, say the OpenMP branch of your code, one of the OpenACC branch of your code. In theory, this works well, but it only works well as long as you stay in one of those branches. Because at some point, you're going to want to merge the OpenACC branch with the OpenMP branch, and you realize both of these branches have touched 500 files, and they've touched the same 500 files, and it's a royal nightmare to try to merge them. And in particular, if you now also have 10 external contributors and everything, this does not work in large projects. So in large projects, I would strongly, instead of favoring this rebasing approach that we use, Linux kind of uses this too, but for Linux Torvalds does this manually. So that every single person developing something for our code base, they will have to, I have my small feature, but I will have to rebase this. The blue part here, that might have been the state last week. And this is the feature I'm developing that is now based on the state of my code base last week. Sadly, why I didn't have time to commit that before I was on vacation. And during my vacation, the code base has now moved. There are 49 more dots here. That means that I will have to take my feature and rebase it on the new last state of master. And until my code is in here, I will have to keep rebasing it, which is a bit of a pain if there are 49 new commits per week here. For this to work, you need to write very small patches. The beautiful thing is that the people reviewing this and other people deciding whether this should go in, they only have to look at one very small piece of code, and that could be applied cleanly, directly on top of the latest state of the master branch. You should never try to merge these gigantic branches with 500 patches, because that's when you get horrible bugs. Good commits are small. If you did the math in the previous, our average size of our commits, which is it's a complicated large code, our average size of our commits is less than 100 lines of change. And the problem is that the time it takes to review something goes up probably by the cube of the size of the patch. If anybody submits something that's 1,000 lines of change code, I can virtually guarantee that it's going to take a month before it goes in. If your change has 10 lines of code changed, it's going to go in this afternoon. So you learn to be disciplined, even if it's only your own repo. Somebody said here this morning about that, oh, you should start to use tools like this when you get a large code base. I would argue the exact opposite. You should start using it when you have 20 lines of code, because it's easy to start using these tools for a small code base. Once your code base is large, you already introduced all those bugs. This is an example from the Laplace code. Tiny change, 13 lines, and of those 4 are blanks or so. It's going to be, if I happen to introduce a bug here with, say, the CMake version there, this would be trivial for me to see in a year from now on what bug Erik added here on July 9th, 2018. And there are, trust me, there is a fair share of bugs and typos in these 40 changes or so I added in this repo. You can follow all of my embarrassments there. The other reason for doing this has to do with testing and these build chains. How many of you are used to build chains? Okay, so that's it. So the reason for having build chains is partly based on what you've seen here. Does your code compile on Windows? Oh, one person has compiled on Windows. If you don't know, the answer is no. I can virtually promise you that, because it's a different compiler. PGI, PatScale, BlueGene, the Fujitsu compilers on the K computer. It's still around for a month and a half. ARM, ARch64 with the commercial ARM compiler, with Clang, with GCC, PowerPC, the big engine, or the small engine version of PowerPC, because there are two, Google native client if you're going to run it in the web browser. If you don't know, the vast majority of these, if you have a large code and you don't know, the answer to the vast majority of these is no, because they all have some peculiarities. And PowerPC can be little engine nowadays too. So just because it says PowerPC doesn't mean that you can assume anything about the engineness of the machine. So the reason for build chains is that most of these things can be controlled with defines, compiler flags, and everything. And normally when you're sitting and playing with the Laplace examples, you start out by running the compiler manually. And then you did with what we saw in the previous session here, that you open your make file, right? And you make some edits in your make files, and there is a mistake, and you edit the file again. And then you do this 500 times, and then you go crazy, and then you give up editing make files. And then you get to the point you realize, I had to automate the generation of my make file. So the proper thing to do with MPI is that you should ask the system, what compiler are you using? And then we should detect with this compiler, what are the commands we should use to execute an MPI job? And that's perfectly possible to automate. And the stuff, there are tons of things you can ask here. For instance, this is the buggy version of a particular compiler or library. Then I want to find out so that I try to work around that bug. How do you create a shared library on this host? I'm not going to go through all of these. There is an old way, if you've ever run those /configure make install scripts, don't do it anymore. It's the old style GNU tools and they're completely horrible to write. A few years ago, almost a decade now, CMake appeared, which is a cross-platform tool that also works great on Windows, and I so recommend that you should use CMake. CMake ends up looking complicated for large projects like GROMACS or other ones, but that's simply because we have 3 million lines of code and we're running at every stupid architecture you can imagine. Forget about GROMACS, forget about this stuff. Look at this simple, this is the entire build configuration for the Laplace system. And this is a build configuration that will automatically detect OpenMP, it will automatically detect OpenACC, it will automatically detect MPI, no matter what compiler you're using the MPI. I have unit test support here. I have a ton of things here. Whatever MPI libraries use, I support multiple MPIs, I support multiple different compiler flags, everything. I have Doxygen documentation, and it's 75 lines in total, including the blank lines. This is easy enough that you will be able to understand it. So again, but then of course, when you need that strange thing, oh, how do I detect a particular version of the FFTW library? Go to GROMACS or some other code and steal that particular file and add that to your own repository. The other thing that I would strongly recommend, that what CMake, the second you start to use tools like this, you automate a whole lot of other things. So for instance, you can automatically get out of source builds. So if I place my Laplace code in a particular directory, that's the source code directory. But you might have something that you're working on the OpenACC CPU build, a GPU build, an MPI build, say builds with different compilers with OpenMP and everything. You can keep all these builds as different subdirectories. And if I now change one small source file, I can just issue make in each of these 6 directories, and they will all update it. For the Laplace code, it doesn't matter because it's one file and it compiles in 1 second, right? But GROMACS can easily take 2-3 minutes to compile. This is kind of neat to have all these different architectures up to date at the same time. And this is automatic. Just create a directory and then you invoke CMake with the full path to the source code, and then whatever options you need here. So we always do this. We never ever build in the place where we actually have the source. The other thing that you're going to need is documentation. How many of you document your code properly? Yeah, I thought so. With GROMACS, the worst thing that happens in GROMACS is that occasionally you have to edit an old file that's 15 or even 20 years old. And then you get so irritated because the stupid idiot who wrote this file has used stupid variable names. None of the routines are documented. For loops in 17 levels, complicated logics, and I can't understand anything to it. And eventually you get so irritated that you're gonna go into Git and look in the original, whoever wrote this code, and you're gonna send them an angry email, and this is committed by Lindahl, January 1st, 1998. Oops. I even forget stuff I wrote myself 20 years ago. And you can't even be angry. I can be angry with my younger self. He was a really stupid student at the time. Documentation. You need to document. This is where you first start preventing bugs. There is only one way to have documentation that's up to date, and that is that the documentation lives in your source, period. If you think that you're going to write this, again, there were 3 or 4 of you writing documentation, you will never write separate good documentation in Word. You will do it once and then you're not going to keep it up to date. So documentation has to live in the exactly same place where you have your source files. And the good thing is that that's not particularly difficult. This is C++, but it also works in C or Fortran. So this is a small class that implements random numbers. What it does is not important. So here we have documentation for the class, 3-4 lines. And then for each method, I have a very brief description of what the method does. The method is just a function call for a class. And then for each parameter to the method, I have a small description what the first and what the second parameter does there, and then maybe a note and a warning here under what circumstances this can throw an exception. The cool thing here is that Doxygen, we have very aggressive settings. So Doxygen will automatically detect and check that every single parameter, every single argument I have in there has to have documentation. If I forget to document one of them, Doxygen is going to give me an error, and later on I will not be able to commit that code into my repo. And when I just run Doxygen, which is going to be as easy as saying make docs, because C makes all that up for you. I will get beautiful web documentations where this is formatted, there are hyperlinks to all the data types and everything. Every single public member function is going to have, and it's always going to be up to date. Because if I add one argument here to this function, but I forget to update documentation, Doxygen is going to complain that there are now 3 arguments, but you only documented 2 of them. This is really irritating at first when you start to write this, and it's really nice when you saw those other 49 patches that were written while I was on vacation, because they will all have perfect documentation. Sadly, I've added support for Doxygen to this Laplace project, but I haven't added the actual documentation yet, and that's why I'm going to need to direct it to the GROMACS. Let's see if we get this working. Nope. We'll have to do that one instead.